Hi guys, today is the Code Jam qualification round, and it should be fun. As more commemoration, I'm wearing my previous Code Jam shirt just to like flex on the haters. But yeah, so I'm just gonna be solving this live, and then as always, going over solutions at the end. And I'm gonna be trying out a new form of solutions, namely where I sort of like do a very brief overview of what's going on at the beginning just to like get the main ideas out, and then afterwards I'm going to go into more detail and possibly prove some things if necessary. For some of the easier problems I may merge these two parts just because they're simpler, but it depends. We'll see how it goes. I will be trying that though. As always, going to update the sub count and fix some stuff. Nope, that's not. Yep, and fix some stuff, and we will get started. Just fixing my template a bit. Yeah, I'll have my code also available in the description and stuff. Everything should be good. There's a clarification apparently. Or not. What? What? 0 plus 0 plus 0 plus 0 plus 0 plus 0. Where's the question? Okay. I am confused, but I guess we'll do that. Okay, so our goal is 30 points, but I'm going to try and solve everything. I guess we'll find out how well that goes. Let's just start. Alright, reverse sort. Reverse sort is an algorithm to sort a list of distinct integers in increasing order. Reverse sort L for I to length L minus 1. Find the minimum value, put it at the beginning. Wait, that will sort it in reverse order. Wait, is this 0 indexed? Wait, what? Is it 0 index? So 4, 2. Oh, I see. Oh, okay, so yeah, you pick the minimum value and then put it at the beginning and reverse the whole array. So the cost is, let's see, n is 100. Okay, that's easy. So we can just like do it. We can just do out the algorithm pretty much. I guess that's how that's gonna work. So we're going to, oh yeah, and by the way, because I'm starting like many hours late, my rank is not gonna be like that good even for solving all the problems, because a lot of people probably have. So we'll see how it goes. So that what that means is the penalty isn't really that important. So if I get a wrong submission, it's like fine. So I'm not going to be trying that hard to do well in that regard. Okay. Yep. All right. So we're going to read in the value n, then read in the array. And by the way, LL is long. And by the way, wait, what? If you have no idea what CodeGem is, wait, did I open the right thing? It's basically a coding competition hosted by Google with many stages. This is the first. It's the qualification round. Right. So they 1 index, I'm going to 0 index. So we pick the first position. Then we find the minimum index. J equals I plus 1, J is less than N, J plus plus. Wait. How does this work? Oh. Okay. It should start at I because that could also be the minimum. Yeah. And then we just reverse the whole thing. I'm assuming values are distinct? Yeah. Okay. If AJ is less than the current value we have, then set that current value to J. Then ants plus equals the length of the subarray, which is the ending position minus the starting position was plus 1. That should do it. I do love that they have this copy paste option. I'm not prepared for multi-tests. That's another thing. 7 to 28. What? Oh, I'm not doing the reverse, that's why. So, let's see. How is this going to work? We need to reverse every. Actually, I can just do this. C++, awesome. A plus I, A plus mindex plus 1. The plus 1 is because it's exclusive of the last part. Forgot I can just do this. C++, hell yeah. Okay, now it's still off by 1, and the reason is unknown because of that. Another way to do it is just to subtract 1, but it doesn't really matter what we do. Okay. Makes sense. Paste it as C++ 17, and we submit. Let's read the next problem. 5.11.1. Cody Jamal is working on his last piece of abstract art, a mural, waning moons and closed umbrellas. Unfortunately, greedy copyright trolls are claiming that waning moons look like an uppercase C and closed umbrellas look like a J. Samples, yep, we got it. And they have a copyright on CJ and JC. Okay. The empty spaces could be filled strategically. I see. Right. So given the costs X and Y in a string, how much does he need to pay in copyrights if he finishes his mural in a way that minimizes that cost? What? Okay. Interesting. So we could do casework. What we could do is we could, let's get out the trusty drawing pad. So say we have some string like this. CJ, like question mark, CJ, C, question mark, something like that. And then maybe like J. Right. So what happens here is when we have this, basically each choice for the question mark is sort of independent. So what we can do is we can say that, like, clearly these three must be equal to each other. Maybe, actually. It depends. If it's negative, maybe not. But for the other verdicts, what we can do is we could say that these three must be equal to each other because the costs are going to be positive. So really we're just determining what are the ends going to be. And yeah, so if we ask what the ends are going to be, well, it's going to be if these two surrounding ones are the same, or if they don't exist, like if we have a question mark on the end, then we want to make it the same as the other ones. And otherwise, if they don't exist, then, or like if they're different in this case here, then we have to pick one of these, either JC, actually the cost is fixed no matter what, so it really doesn't matter. So that's interesting. Yeah, that's kind of cool. So the cost is fixed, so that's even better. So really, we just need to make all consecutive question marks the same. So if we like compress all the question marks into like a single question mark, because we know they have to all be the same, then the choice is just either if the surrounding two are the same, then we make it that because the costs are going to be positive. Again, this is only for the first two, not the last one. Or if they're not, then we can, the cost is fixed. Either this is a C and then we get the JC here, or this is a J and then we get the JC here. And similarly for here, if this is a J, then we get the same cost here, and if this is a C, then we get the cost here. So it doesn't matter what we do for the question marks. So actually, this is equivalent to just removing the question marks. That's cool. That's cool. Yeah, this is equivalent to just removing the question marks. In fact, I might submit that now. This is interesting. Okay, so I like I said, I don't care about penalty. So to prove that this solution works, I'm gonna try it. So C into X, and then Y, and then the string. String T is something else. So we just make a new string with everything but the question marks. And then t plus equals c. Then we store the total cost. I is less than n. No. T dot length. Except also we're comparing the next character, so we need to not look at the last character, because then like if we're processing this one, then looking at the next one would go out of bounds. So we only iterate up to here, not to the last character. Let's see. If ti is equal to c and ti plus 1 is equal to j, then we get the cost of, what is it? X for cj. Otherwise, if this is j and this is c, then ans plus equals y. This is interesting, yeah. So this would be like quite a cool solution for this problem if it works. So I'm gonna submit this, and then I'm going to go over the solution that would handle this. This solution is wrong because for the negative, if values are possibly negative, then we may want to convert some of these to like, for example, in this case, say we have c question mark c. If x, which is the cost for cj, is equal to like -5, and y, which is the cost for jc, is equal to like 2, then even though we could make this the same, we don't want to. We would want to make this a j, and therefore we have a cj, which gives us -5, and then a jc, which is 2, which would give us -3, which is the best, because we want smaller numbers. So if we have many question marks in a line, it's also true. It means that we don't necessarily want all question marks to be the same. I will also go over that solution, but first I just want to submit this and see if it actually works, because that would be funny. Just like ignore the question marks entirely. Also, I don't know why am I in Japanese? What? Windows key and space. I forgot how this works. Okay, yeah. Yeah, so it gets that. It's going to get this test set wrong. So I'm going to resubmit it now, because I know this gets this test set wrong, but it does still get the first two test sets. So that's cool. Let's see. So this is the first solution. So now what we're going to do is we're going to do better. Basically the idea is, actually, why did I get rid of that? That was not smart. Okay. Alright, so we leave the question marks in. This is going to be a mess. Let me just try and erase these. Oh, the glory of using paint. It's bothering me. Okay, right. So that was a struggle. So what we're going to do is, say we've solved for like the first 4 characters. Now, when we're deciding what to make this character be, like, what do we think is important? So we know the cost for solving for this character, solving for the first 5 characters, is going to be whatever the cost was for these adjacencies, plus this extra one that we now get from adding this one in. Actually, let me get different color coding. So these were the previous adjacencies of the string, and now we get this new one because now we're adding this character onto the end. So really the only thing we care about from this previous string is A, its cost, and B, the cost of this adjacency. And the cost of this adjacency depends on 2 things, this character and the previous character. So really all we're asking is, for this string, for both of the possible previous characters we could have had, for example, this can be C or it could be J, what's the best we can do? So if we define some function f to be like, to say f of, let's call it I and j, because that's loop stuff, is equal to the answer for the first I characters. It's also dynamic programming. It would be the answer for the first I characters, and then with the last character being j. Then the thing that Fij represents is going to be like, say we're solving for some string, and this is the last character. For example, say this character is C. Then like everything else doesn't matter. The only thing that matters is the total cost of the string and whatever the last character is. So of course you can replace f with like dp for dynamic programming, whatever you want it to be. But that's the basic idea. So then with Fij, we can do two things. We can stick it, actually no, we can do one thing in two different ways. So now what we do with Fij is we stick a new character on. So then say we stick on C, if that's possible, then we're going from this string, whatever this string is, to this new string where this is, say, another C. So then now, because this is now the new last character, this character becomes irrelevant. So basically the new string that we're solving for is of length I plus 1, and the last character is C. So f of I and j can transition into either f of I plus 1 and C, or f of I plus 1 and j, depending on what we do. And in either case, the new cost we have is simply this previous cost plus the cost of sticking this character on, whatever it is. So then, because we know that, for example, f of 0 and, like, for example, what would this be? I don't know, like f of 0 and c. Say the first character is c. Then we know that f of 0 and c is 0. And then we set, like, we initialize everything else to be something like infinity because we want to minimize it. Then what we can do is to transition from f of 0 to f of 0c to f of 1 and some other character, we simply do out these transitions. So the way this would work is, let me see. So basically we're going to compute this out where we have 1,000, okay. But this will work in linear time. So cn to x and y and s. So if s0, if the first character of s is not equal to c, yeah. So we use 0 to represent c or j, and then actually 0 to represent c, 1 to represent j. So this would be, if it's not j, then the first character can possibly be c. Because either, if it's not j, then it's either c or a question mark, and either way it's possible for it to be c. So first what we do is we use memset. And basically the way memset works, it's some sort of bitwise magic that I'm not going to go into that far. But basically setting it to 1 will actually basically be equivalent to infinity. So it's going to work. So then f of using one character and having it be c can be 0 because it's cost 0. If it's not equal to c, then it's either j or a question mark. Either way, it's okay to have the first character be j, so we set that to that. Then now we consider every new character. Yeah, so first case is sticking on a c. So this is also the same thing. If this current character is not a j, then this could possibly be a c, either be a question mark or being a c directly. And therefore, we do some transitions. So we're going to, once again, push out this f of ij into a new state, f of I plus 1 and c. So f of, let's see, it would be I plus 1, and then the new character we have is 0. So we do that. Again, this is dynamic programming. If you're interested, I do have some other videos on that. So possibly check those out if this is confusing to you. So if the previous character was a C, then we have no additional cost. Actually, this should be min, I bet, because we want the minimum cost. And then otherwise we can stick on the first character. Otherwise, all right, sorry, so I'll comment this in. So the previous character was a C in this case. And if we have f of I1, then the previous character was a J. And therefore we have the cost of J and then C. Should be Y, right? Y is JC. Indeed. Okay. So the cost then is Y. Then we do the same thing here. We stick on a J. F of I plus 1, 1, because now we have that character. And then same transition. So this is if the previous character was a C. So therefore it's f of I 0 plus the cost of having CJ. And also the previous character could be a J. In which case we have no cost. So then the answer is the last character can either be a C or a J, so we consider both. So it's the minimum of the having n characters. N characters? Yeah, having n characters. So n 0 and f of n and 1. I don't know why I have two mins. That doesn't really make sense. Cool. Okay, that's fun. What's with that? Cool. Well, actually, here you can see the value that you get from memsets. Oh, right. I need to define n. There we go. 5, 10, 1, 0. Here we get this. Should get -8. There we go. Now this solution should pass all of them, even the ones with negative numbers. So again, this one, it's enough when all the costs are positive to literally just ignore all the question marks, because either way we'll make it so all the question marks are the same, and then we can make it equal to either one of these. So it's equivalent to basically removing them. Or we can do this dynamic programming solution for the extra credit. So let's submit that now. Should be accepted for even the hidden case, because again, this one will certainly fail the hidden case. I know that for a fact. Like, I probably wouldn't even work on that sample. So there we go. I see no reason why it wouldn't work for negatives, because it's simply, this is just infinity anyway, and we're working with 1,000. So we should be good to go. And I think that was enough of an explanation that I don't have to do another one at the end. So this should be good. I'll interleave these solutions. All right, Reversort Engineering. All right, so what's the difference? The main parts are identical except for the last paragraph. Okay. Find a list. Oh, okay. Find a list of n distinct integers between 1 and n such that the cost of applying reverse sort to it is exactly C, or say that there is no such list. Is n 1,000? Okay, good. Because if n was 100,000, this would require a very annoying data structure called a treep, and I don't want to do that. Right, so if we have a cost too big or too small, it's not going to work. The cost has to be at least n minus 1. And let's see. This is some permutation stuff, isn't it? All right, so the basic idea for this solution is, say we have like, oh, that's a lot. What? Paint, man, does some stuff. All right, so I think this is too zoomed in. Yeah, that's still too zoomed in. Okay, so say we have a cost of like 7 and 6. Um, the main idea is what's the input? The cost is C. So the constraint is that first C has to be greater than or equal to m minus 1, because for every step of the algorithm, we do at least one reversal, or we reverse at least one index. So we do m minus 1 steps, and each one takes at least one cost. So if we have less than m minus 1, it's automatically not possible. And in the other case, let's see, how would this work? Oh, I see. Did they just take the samples from the first problem and like reverse them? Is that really what they did? Yeah, they just did that. That's funny. Okay, cool. That's funny. Anyway, 24 points. So solving this would be enough. Let's see. N being less than or equal to 7 will just give us like straight up. It's the like try all permutations and have it work. Yeah. Okay, but that's not interesting. So what's the upper bound on the cost? Well, theoretically, say we have 7 spots. With a theoretical array, the minimum element for the first one can be here, meaning that we would have to reverse the entire array for the first step with cost 7. Then the theoretical second element could be, now we sort of like remove this index. Now the theoretical second smallest element could also be here, because this could be reversed. This whole array would be reversed. So whatever would be here would now be mapped to here. So then theoretically we could have a cost of 6 here to reverse this whole thing. Then once again, the theoretical smallest element could be here, and we remove this, and then we get 5, and we get 4, and 3, and 2. And we can't get 1 because we don't do an operation for the last element. So really, the cost is the sum, like 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, except we exclude the 1, so we subtract 1 from that whole thing, which is well known to be like, these are triangular numbers, so this is n times m plus 1 over 2 minus 1. So that's the upper bound, because we can't do any better than that. So C must be between m minus 1 and the upper bound of n times m plus 1 over 2 minus 1. 1,000. Wait. n plus, yeah. Yeah, we're fine. Okay. So the basic idea now is, what we want to do is we want to construct this array. So the basic idea is we can do some sort of greedy, and basically say we have, we know the absolute maximum we can get from these numbers is like 1, or is like we can get any number between 1 and 7 for the first operation. We can get any number between 1 and 6 for the second, 1 and 5 for the third, 1 and 4 for the fourth, 1 and 3 for the fifth, and 1 and 2 for the sixth. I can't count for some reason. Okay, that's weird. And say our initial cost was C, then no matter what, we're going to have at least 1 for all of these. So we might as well just like do that from the beginning. So we set C to C minus n minus 1. In this case, it would be 6. And therefore, now we can we assume we already handled these costs of 1. So now we're really just saying, now our costs are from 0 to 6, 0 to 5, 0 to 4, 0 to 3, 0 to 3, 0 to 2, and 0 to 1. Then we can pick any number in between these. So now we might as well just do whatever we want. We might as well say, let the remaining cost be x. Then if x is between 0 and 6, then just have this be whatever x is, and then everything else will be 0, because that's how much we have left. The remaining cost we have left is x minus x, which is 0. If x is greater than 6, then we can simply do the whole thing, and then x becomes x minus 6, and so we take 6 here. And then now if x minus 6 is between 0 and 5, then we can make this whatever the remaining value is and have the rest be 0. Or we can continue. We can say we'll use the whole 5 here and continue on until we get to the end. And because we've already guaranteed that we can do this, essentially we can get any value in between m minus 1 and that. So the basic strategy is to do greedy. And the reason this works is some form of continuity. Like, say you start from the minimum value, then the strategy is you can get, like, let a be the minimum value, like the minimum value that we showed before is m minus 1, and then b is the maximum value, which is m plus 1 over 2 minus 1. Then we can get any value in between a and b by simply saying, let's start with the minimum cost for each of them. So for example, say these are all 0, 0, 0, 0, 0, and 0. Now at any point, we can change our operation in such a way such that we increment the cost by exactly 1. So we make this 1. Then we can increment this to 1. Then we can increment this to 2. Then we can increment this to 1, then to 2, then to 3. And it should be clear now that because we can change it by 1 every time, we can get every integer value in between this, as long as it is in between that. So that's basically the proof for why this works. But that's the idea. I guess I'm not doing that new format. I guess I'm just like sharing these solutions as we go. All right, that's the plan. So now we just need to figure out how we actually like do this. So let's see. So say we have an array of 7, and we have a cost of, for example, n equals 7, c equals 9. So we first subtract m minus 1 from c. So we start with x equals 3. That's not a great example. What if we do better? What if we do like c equals 17? So we set x equals 11. Now we can get a cost anywhere from 0 to 6, depending on where we place the 1, because the 1 is always going to be the minimum element. So in this case, we might as well put the 6 down. What if I want a different number. I'm gonna make this 18 instead. X equals 12. Yeah, you'll see why. I just want to make it a bit more strong. So we're gonna put the 1 here. Yeah. Let's see. So actually, because n is 100, we can do this naively. We're gonna put the 1 here. So then we subtract 6 from our total. So x becomes 6. And then we reverse this whole array. So now this index is kind of gone, and now we're interested in, like, where can we put this now? And the basic, or like, where can we put the 2? And the basic idea is, again, we want to put it here because that'll maximize our cost. So now this 1 is sort of gone, so we can assume the 1's just here and it will be happy and it'll be done. And then we can figure out where we need to put the 2 here. Except we know that we reversed the array beforehand. So to figure out where the 2 would actually correspond to in the original array, we need to simulate the reversals until we do all of them, and then we make the 2 happen. So for example, we would reverse this whole array, and then the original index of the 2 would in fact be here. So now we subtract 5 from that, and then we get x equals 1. So for the last position, now this position is gone. So for the last one, find a different color. We want the cost to be 1. So again, because we subtracted 1 at the beginning, this is now 0. So if we put the 3 here, then that will work. Except now we know we reversed. First, we reversed the last thing we did is reverse the orange array. So because we're doing the reversals in reverse order, we need to do them backwards. Because we're starting at the end and we need to figure out where this would be in the beginning. So this is asking, we have this 3. Where do we need to put the 3 in the original array so that after we do these 2 reversals, it ends up here? And therefore, the way to do it is to simulate the reversals backwards, because the inverse of a reversal is a reversal. So that's fine, we can do that. So we say we're going to put the 3 here. Then the cost decreases by 1, and we end up with x equals 0. And then now we figure out where the 3 has to be originally. So we do the first orange reversal, or the last reversal that would have been done. So now the 3 ends up here. and then we do the reversal that we would have done first in the original order, and so the 3 ends up here. So we know the 3 has to be here in the final array. Again, we know the 1 has to be here, or in the original array, and the 2 would have to be here. Then we do the same thing, and we keep going along. That's the strategy. So we can figure out where the numbers are going to be in the original array. So let's do that. What I'm going to do is, so I'm going to have a location for that, and I'm also going to store the, I'm also going to store the right index of the reversal we did for each reversal. Like, for example, for the first, we reversed this to this, so I would store this because we already know this. But I do need to know this so that I can store this reversal. And for the second reversal, we know it's going to be this and then this, so I would store this once again. Then for the third, I know I reversed this array to this array, so I would store the right point. And then I can easily simulate the reversals once again. Cool. So, yeah, I got rid of the case number. Right. So c into n and to x minus equals n minus 1, just for the, actually wait, first we do the checking. If m minus 1, if it's not within the bounds, so it's not between m minus 1 and that, n times m plus 1 over 2 minus 1, then the answer is impossible. Yeah. And so note this little trick I'm doing for like checking within an interval. It checks like the left bound and then the right bound, because we can't merge these, but we can basically like do a similar sort of syntax. So even though it's like sort of like a, what is it, a Yoda operator, whatever that is, or Yoda comparison, it like makes sense to do it like this. Okay, so now yeah, basically we figure out where this would be. So the location equals, first, if the cost again is between 0 and this, then we would put it in the position of the current index, and then if the cost is c, then we have to take c steps forward. So it would be I plus c. So it's the minimum of I plus x and the upper bound on the cost we have, because we can't go outside of the array. So the highest possible cost we can ever represent is the highest number of steps we can take, which is equal to, this is m minus 1 and this is I. So the cost, the upper bound is n minus 1 minus I. So we get this, and that should be right. Yeah. No, wait. Actually, it should be I plus this. And so if we get rid of the minus I, then it just cancels out to n minus 1. And actually, this makes sense. The location is either in the array, or if it goes outside of the array, we have to take the minimum and bring it back inside the array. So actually, I'll call this position. Then lock I is equal to position. Then the effect on the cost this has is it's the difference between the position we sort to and the index. Normally we would add 1 here, but because I already do this at the beginning, it just works out. And the reason I do that is to make the math slightly more convenient. Because otherwise we'd have to figure out like where we are, and then this would have to like take into account that we need to have 1s everywhere else. It's just annoying. There's no really reason to do that. So now I'm going to do a trick. We don't care about what's happening in the array. Or actually, wait. So then the next step is the index of the ith element, which is conveniently I plus 1. So it's, for example, 1, would be, actually, we don't know that yet. So basically what I'm going to do is I'm going to say a position is equal to like -1. Or actually, rather, set everything in the array to 0. Then set this to -1. and then we're going to do the reversals out and then find the location of the -1. And that would tell us exactly where this element ended up in the original array. So for every reversal that we've done previously, from I-1 to 0, be careful to decrement the right variable here. We reverse from j to the location of j. No, wait. It should be a plus j, a plus location of j plus 1. And again, just plus 1 because it's exclusive. Okay, wait. I need to. This technically isn't a problem because of the way it works, but I'm still going to do it for clarity. So if aj is equal to -1, then b equals j. You can do a break. It doesn't really matter. It's n squared anyway. Actually, this makes it n cubed, so it's even better. You could, I mean, theoretically, like just do the math to figure out where j ends up, but the point is to make the implementation convenient. So it really doesn't matter. We have 10 seconds. It's fine. So yeah. So now we know this is the index now. So the index of I is equal to v. So now we create the original array by setting the indexes. So a of index of I is equal to I plus 1, because again we need to start from 1, not from 0. And then we just print the array. So let's do it. See if it works on these. It should. Does it? Doesn't seem like it does. Okay, that's a problem. So we wait, what it? We get 4, 3, 2, 1. Let's simulate that. We end up getting the right answer here. So we get 4, 3, 2, 1. So we reverse the whole thing with a cost of 4. Then we get 1, 2, 3, 4. Oh, and it's sorted. Okay, that does work. Okay, let's try 17. 1. So what was it? 7 and 18 actually. So we should get something like, we know 2 is in the original position. We know 1 was here. We know 3 should be in the third position. And everything else sort of just works itself out. Test the edge cases. So 1. So 3, the minimum cost is 2. Actually, wait. 2. So 3, it's 2. We can also have 3. Or the upper bound is n times m minus 1 over 2 minus 1, which is 5. So if we do 6, wait, I keep adding this. So 3, 2, 3, 3, 3, 5, 3, 6. Yep, and then one more for that, should be impossible. So here, once again, this maximizes the total cost, but for 6, it's not possible. I don't actually know why I'm being so careful, because like we're gonna submit it anyway. There's no penalty, so I guess it should be fine. If it doesn't work, I'll debug it, but I don't really care. I'll just YOLO it, I guess. Cool. All right, interactive. You want to sort n distinct items. Unfortunately, you do not have a way of comparing 2 of these items. You can take 3 of them and find the median. That is the one that is not the minimum or the maximum. Okay, it's distinct. Come on, judge for me. So you want to sort n distinct items. Unfortunately, you do not. Why am I reading the same thing? So you can take the median of that. You can take the median of that. You can take the median of that. Cool. Works. Yep, alright, so that concludes that. That was another problem. I think that also suffices for the explanation, so I'll leave it there. Yeah. Did I go over the first one? I don't think I did that well. I don't know. The median question is the same result for any 3 elements in both cases. It is impossible to distinguish the order of any list from its reverse. Interesting. Really? Huh. So we know x1 is in between x2 and x3. x2 is in between... Yeah, I see. Okay, interesting. Right. So your program will have to find the order of t lists in n elements using at most q median questions in total. So what? Is this one of those like ones with weird bounds? Oh, on average, so it's random. Okay. So 300. Wait, so what? Oh, I see. Okay, sure. So with this first case, it's basically just, yeah. After receiving the judge's answer for the teeth case, your program must finish in time and not to receive a time limit exceed error. So it's random. That feels important. Is it important? Alright, so what's our strategy here? So for n equals 10, what's the order here? So 10 choose 3 is that, so that barely works. 50 choose 3 is absolutely not going to work. So say we know the median of the first 3 elements. What can we do with that median? So if I get rid of this is where it gets interesting. So does it give you the values? Oh, wait, what? Oh, it gives you the index of the median, because it doesn't really matter what the... Okay. Wait, what? So all test cases are independent. Oh, no, it's... Okay. Okay, that's weird. Yeah, it must be like random stuff, I guess. So it utilizes randomization, which is something I'm going to have to deal with. Right. So we know the median, let's just draw some stuff out, I guess. So we know the median of the first 3 elements. Just to confirm, we do not know a way to compare the items. We are given 3 of them, we can find out which one is the median. Okay, is there a strategy we can use to like find the first element or something? Not exactly. We can find which elements are in the middle. Let's see, log 50 over log 2. Interesting. So n log n is feasible. No. Is it? Not really. Can have a way of comparing two elements. That would be interesting, but I don't think that works. It takes too long. So if we query the first three elements, now say the median is x. Like say the median is a. I might spell out some letters here. Now, is it interesting to use the median or to not? We can like put an element in between two other elements. Like we know if the median of these three is this, then this is going to be in between whatever these two are. So this is like 1, 2, 3, 4, 5, 6, and 7. We know our final array will look something like 1, and then 2, and then 3, or maybe the reverse order. So what can we do with that? Can we find out like what's in between this? We can like partition all the elements based on how they are relative to 1 and 2. So if I query every element with 1 and 2, then that gives me something like this. Then for example, we can figure out if other elements are between or... Actually, we don't know which side... No, that's not helpful. We don't know which side they're on. Actually, wait, do we? Yeah, we can assume like 1 is less than 2, I guess. Then we do know which side they're on. If 2 is the median, then it's over here, and if 1 is the median, then it's over here. And then if that other number is the median, then it's in here. So what does that tell us? Does it like give us a way of doing smart things? On average, that splits the array into thirds, I guess. Is that what we're supposed to do? Really, like just trust the average? Log 50 over log 3 times 50. 178. 178. Is that what it is? Is that what we're supposed to do? Now we have 3 separate arrays, and we partition them like this. It's like, how bad is it? It's like each element takes some query or something, right? Let's see. C++ shuffle. Okay, sure. So that works. I have this random number generator. Let's have it use a seed since it doesn't really matter. I can write a tester for this. Do they have an interactive runner? It's in Python. How does this work? that's not very helpful, I don't think. I'll just write this myself. Did I print the case number? Is n, okay, n is not 3. That would be confusing if it was. Right, so let's just do this. I mean, there's like a smooth way to do this, and there's like a not smooth way to do this, right? It's like 3, 1, 2, 1, 3, 2, 1, 2, 3, 3, 2, 1. Okay, we can do this. If AI is less than aj, swap ij. We do the same thing for this. We do the same thing for this. It's kind of like a bubble sort, I guess. I don't know. I mean, there are better ways to do this. I just like don't know. Let's see. So iota will fill it from 0 to n-1, like in that order. So index I will get the value I. And shuffle is just simply shuffle it. Yeah. So basically, like, get rid of that for now. That will comment out later. This is all just for like debugging interactive stuff. Do read in that. This is interesting. I'm messing with my template now. So into tests, then the number, then the queries. Why do we need the queries? Is that useful? I don't know if it is. Okay. So now we're going to, what do we need to do? What do we need to do? That is a question that should be answered. I don't know. What am I doing? Okay, I'm gonna just like archive this because this is my old template. And we'll have this new thing here. Don't need that either. So we do generate. Yeah, then solve. Cool. Now what we need to do here is we need to say Just thinking about implementation details here. I think this should work, and if not, I can fine tune it. Because it does, on average, like pretty well, because for a problem of size n, it takes m-1 queries. So if we split it up into like 3 groups, it'll take m-3, and then on average m-9 and m-27 and so on. So it should theoretically be like pretty good. Maybe. I don't know, maybe. Because it's random, that's the thing. So it's random, so it's like it doesn't... We're still recording, right? I always do these sanity checks. So it's random, so it shouldn't matter that much. My face... Oh no, I've just been like hanging out down here. Maybe this is a better angle. Okay, so that was a thumbs up. So I guess, yeah. Okay. So the first thing we're going to do is, the initial array is a special case. So first we're going to do this partition like this. Then we end up with, so we assume a sub 1 is less than a sub 2, because it doesn't matter, otherwise it will be reversed in any case. So then we have 1, and then 2, and then we have 3 groups. Now this is the now that we're solving for a group, what are we interested in? First we need to pick 2 numbers. So if the group has only 1 number, perfect. If the group has at least 2 numbers, then we pick 2 of them arbitrarily, call them x and y. Now we need to compare x and y, because we can't have the reverse of this. We need the actual answer. So what we can do is we can use either of the parents. Now the one that's the median is the one that's closer to the parent. So if the parent is smaller, then we have 1 x and y. So whatever's the median is going to be the smaller one, and if the parent is larger, then whatever's the median is the larger one. So now we ordered x and y. So now within this group, we have, once again, a bunch of things. Then we can partition this into 3 groups by doing that. And again, the way we partition them is we ask for x, y, and I. And then the position of I will tell us everything. If I is... Actually, it doesn't? Wait, how do... Yeah, sorry. So because we assume x is less than... I had the same existential crisis before, and then I realized it's fine. So if we assume x is less than y, and in fact we can, and again, this ordering is based on the relative ordering of the parents. So it all comes down to this assumption that a1 is less than a2, but it's fine because we can reverse it, I'm pretty sure. It should be good. If we do the wrong comparison, if this is less than instead, it would mean that the result we get is flipped, and therefore it'll be the reverse of that. Yeah. Because if we have say we query 1xi, xy, assuming 1 is the smaller one, then we get x as the median, so we assume it's smaller than y. But otherwise we would have queried xy2, we would have still gotten x as the median, and therefore x would be the larger one, so it would be the exact opposite. So that's fine. As long as it's the opposite, that's fine. So we ask x, y, and I. Now if y is the median, then we know I is here. If I is the median, then we know I is here. And if x is the median, then we know I is here. So we split it into 3 groups. Then we can solve these 3 groups recursively. And in total, we transition from n to n over 3 each time on average. So on average, it takes log base 3 of n times log base 3 of n, big O, which is not necessarily the greatest bound, but we can make it better because, again, for every problem of size n, it takes n-1 moves. So we can theoretically sort of do this kind of thing where we subtract out a lot of them, and it gets easier and easier for every subproblem we have. So that's the idea. So let's see. Let's just write a very quick just append B to A. that's it. Because it's going to be useful. Right. So first, x equals 0, y is equal to 1. Oh yeah. I'm going to use this. This is my local stuff. So if this is local, then do this stuff. Hashtag else. Do the normal thing. We don't need to do the generations, I guess. Yeah. I guess it doesn't really matter, actually. Does it matter? No, it doesn't. It really doesn't matter. So I guess I'll just not try and overcomplicate things. Yeah, that's fine. But we do need to do that here. We can keep track of the total, that's fine. No, that's not what I want. I need this. Then... So if we're local, do it directly using our array values. Otherwise, endo, because we need to flush, then cn to m, for example. Then we just return m, right? If m is equal to -1, exit, and then get wrong answer, return m. Should work, right? We get a single integer. Yeah, okay. Cool, so now we do this stuff. Vector, ll, left, mid, right. Then for each element from 2 to n, ll z equals query x, y, and I. Order doesn't matter. Now we can determine this based on our cases. So if z is equal to x, if x is the median, should be m-1 actually, because I'm going to 0 index. So if z is equal to x, then if x is the median, then I is in this bucket. So left.pushback I. Otherwise, if z is equal to I, note that these will never be equal. So then if I is the median, then it's going to be here. What did I just undo? Okay. I just undid something, but I'm not sure what that was, so hopefully it wasn't important. I. Otherwise, oh no, I'm just too lazy to write out if statements. So otherwise, the median is y, and therefore I must be here. And again, if we're wrong about a1 being less than a2, then this entire thing will be reversed, and therefore it's fine, because we're allowed to print either the answer or it's reversed. Okay, and we also have one for ants. So now we have whatever's on the left conjoined with x, conjoined with whatever's in the middle, conjoined with y, conjoined with whatever's on the end. So first, merge ants, and we're going to define some solve function. And then we need the two parents, p1 and p2. So we're going to solve for the left. The left parent would be nothing, so we'll say it's -1, -1, and the right parent would be x. Then ants.pushback x. Then once again, we actually wait, ants Yeah, we should do that. Solve for the middle, then the left parent is x and the right parent is y. A lot of this code is repetitive, but I'm just writing it out just to make sure it's accurate. Ants, and then we solve for the right, where the right parent or the left parent is y and the right parent is -1. Now we're going to solve, and it's almost the exact same code. Almost. Let's see. If ins.size is equal to 1, then return ins, because there's nothing we can do. We already know we have one element, so we know its order. Otherwise, y is equal to ins 1. So we do a comparison. If the first parent is not -1, and we guarantee that the first parent is going to be the one on the left. So if we're solving for some group, then this is parent 1 and this is parent 2. And therefore, if we use the first parent, then whatever's the median is going to be the smaller one. So we want to have it in the end so that x is less than y, so that we can use similar code to this. So we ask for the parent 1, the x and the y. Now, if the median is, we're interested in, if y is smaller, then we need to swap the two. So if the median a is equal to y, the median is the smaller one. So if z is equal to y, then we know y is smaller, and therefore we need to swap the two. Else, if p2 is not equal to -1, my bad, it should be fixed here too. So with the second parent, so we get a and b, the median we get is going to be the larger one. So if x is the median, then x is larger, so we need to swap it. So if z is equal to x, then swap the two. So now, it's basically the exact same code, actually. Like, this is pretty much the exact same code now that we do this. Because you should realize, like, it's basically the exact same thing. We have two center indices, and we're solving for the rest of them and breaking them into 3 groups and doing the same thing. So really all we need to do is change this to this, ins I, every time. And then this should be ins.size. Then yeah, so now that's it. Now to verify, what we can do is we can say for LLX ants. Oh, and also we want to print +1. For the answer, you want to make sure it's sorted. So it's like bx is equal to I. No, wait. I equals 0, I is less than n, I plus plus. So we know the ants of I is going to be the index of I. So b of ants of I is equal to I. So then if b0 is greater than b1, then we reverse the whole thing, because it could be reversed as well. b plus n. Then we can do something like, this is a thing, right? Yeah. Sort is sorted b plus n. Cool. Now that basically checks if it's sorted or reverse sorted. Okay, no way this compiles first try. Because I called it ask instead of query, so I should probably like do that. Yeah. I don't know why I'm inconsistent with myself. Like I define my own standards and I forget about them. I should return ants too. So let's just see. For now, I'll just have it read an array. I equals 0 is then ni plus plus cn to ai. Yeah, okay. Should be good. Let's see. So let's generate a test now. So we have one test case, n equals 5, for example, and q equals, like, I don't know, doesn't matter, 0. Q doesn't matter for local stuff. So the array should be, what's the initial value? X1 is the median of, okay, so 1 is in position 4. No, wait, so 3 is in position 1. 2 is in position 2. What's in position 3? 4 is in position 3, 1 is in position 4, 5 is in 5, right? That's how it should work. Because if x4 is 1, then 1 is in position 4, yeah. Okay, let's see. Nice. Alright, so where do we go wrong there? Less than a good one. That would be a problem. Because we can get caught on 0 and then just be totally screwed. Okay, assertion is sorted failed. What are we printing? What am I printing? If def. What am I printing here? Am I printing the wrong thing? No, wait, what? What am I printing? I don't have gen. Shouldn't do that. Is this the answer? Oh boy. Alright, this is gonna be a pain. What am I printing? God, what the hell is that? Alright, so what's happening? So 3 and 2, right? So nothing should be in between. Except everything is in between, apparently. So that doesn't make sense. This should in fact get the reverse array. Don't know what's up with that. That is very weird. That should not happen. It is indeed very weird. So 4 should be on the upper end. 1 should be on the lower end. That should be that. C out Z. Did I mess up the... I can't read this. Okay, so we get 2, 4, 3, 2, and 4. Which is very wrong. So I don't know what's up with that. That does seem like a problem. Very high is less than... Oh wait, shoot, this should be greater than. Although it actually shouldn't make a difference. So I don't know what's up with that. So swap these two, swap these two, swap these two. We're basically sorting them with 3 swaps because I'm too lazy to do it. Like, I don't know what's up. What's up? What's up? So ask 0, 1, 2. That's actually correct. Why does printing it fix it? What? Why would printing it fix it? Oh my god. Okay, so 0, 1, and 3. The median should be 1. So I don't know what's up with that. 0, 1, and 3. Alright, this is stupid. I should not do this. This is dumb. Like the way I'm doing this is dumb. There's no... I didn't compile it. Okay, so 1, 0, 2. That's correct. 1, 3, 0. 1, 3, 0. Why does this not work? Am I doing the swaps in the wrong order? I feel like I am. You know what? This is stupid. Let's not. So we're going to just like... sorted is equal to... I'm just going to make pairs of the indexes and indices and the values. That's what I was planning to do originally, but like... I thought I could do that, but I guess not. I think it would work if I did the swaps in the right order, but apparently they're not. If I had 2, 1, and 3, or no, 2, 3, and 1. Yeah, whatever. Sorted 1.second. I can speed it up by not using vectors, but it doesn't matter. Okay, now, so 2, 4, and 3. Good. Okay, that's correct. So now this is good. So now it's returning the right things for the queries, now that I'm stopped being stupid. So left, mid, and right are correct. Okay, so now we need to solve for these. So none of these should ever have a problem, right? None of these should ever have a problem. So where's this going wrong? This answer is empty. That makes even less sense. Am I screwing up merge? For LLXB, A dot pushback X. Return A. I don't know what I could be screwing up there. For each thing in B, push it to A. Return it. Is this the problem? Very sure this is not going to compile, but worth a shot. 4. Do I need to have the type on there? Yeah, I definitely do. Okay. So that works fine. Merge is fine. That's not the problem. I don't know what's up with that. See if it's doing this correct. Four and two, that is correct. Okay. Yes, 1 is less than 4. One is less than 4. Wait, actually, it should be wrong. 5, yes, 5 is greater than 4. Good, okay. That is correct. I'm just gonna have to like keep adding on print statements until something eventually makes sense. I guess that's what we're doing. All of them are empty? Okay, left, mid, and right should be empty. Oh, wait. Oh my god. Why would I put this in the why would I put this in the loop? Oh my god. Oh, you guys must have been screaming at me. If you were, I'm sorry. I'm sorry for the pain that might have caused you to just stare at this bug for so long. And god, that was stupid. That was so stupid. Okay, 53124, 53124, perfect. The assertion still fails. I don't know what's up with that. B ants I is equal to I. It's because it's what? 23140. Hmm? 53124. Should be 4. Wait up. Oh wait, that's not how permutations work. Okay, I can't reverse B. I have to try reversing ants. So, let's see. So if, then we can return and be happy. Otherwise, try reversing ants. Yeah, that is not how permutations work. Now try it again. And otherwise, now we assert false, because now it's like that's not something that should happen. Okay. 53124. Five, 3, 1, 2, 4. It's not printing it? Why are you not printing it? Did I not compile right? What did I do? It's not, I should put the space before, but that doesn't matter that much. Now it prints it. 21304. That's dumb. 21304. 23140. Five, 3, 1. Okay, get rid of that +1 for now. Makes it easier for me to look at because I'm used to 0 indexing. So 42013. So position of 2 should be 0. Now that, is it the reverse? Now I'm confused. Oh wait, it means x1 should be 2. X1 should be 2. I'm confusing myself. I hate permutations, man. They always do this to me. They always like confuse. They always throw me off so much. This is wrong. It means that like, value 3 should be at position 1. So if we're at 3, wait, what? Value 3 should be at position 1. No, wait, value... I'm so confused. No, the first value is 3rd. So this should be AI, the original array. Right, because we do know the array. And it's still wrong. Now that makes even less sense. I don't know why that swaps the 2. What? The thing in the 3rd element. I'm so thrown off. I'm so thrown off. I'm so thrown off. It should be A of ants I. That also seems plausible. I'm really just trying things until something works. So we know that ants of 3 is 1. So the thing at position 3 should be equal to that. Ants of 3 should be equal to the position that corresponds to that. So this should be I instead. The thing at the 3rd position should be the value that corresponds to the first, to the answer at that position. I don't know, man. I don't know. I don't know what I'm doing. I hate permutations. Okay, it works. Fine. Alright, now that works. So that's good. Makes sense, I guess. I don't know. Okay. Let's try this now. So 1, 10, 0. Am I printing the... What am I printing? What am I printing? Oh, I don't need that. Okay. So let's try like 10, 10, 0. 10, 10, 0. Comp. Might as well just do this. So this is going to be 300. So we have 100 tests, n is 10, we have 0 queries. 1546, cool. So we have 50, 100 tests, n is 50, 0 queries. Let's try again. Random, right. So now we shouldn't use a seed. 150, 0. Let's just try it a bunch of times, hope it gets below 17,000 each time. Seems like it will. Seems like it's doing pretty well. And these are, again, random arrays. So that should be good. Alright, I guess that makes sense. So yeah, we're basically saying bi is equal to the array of the answer. Yes. The thing at position 3 should be the thing that corresponds to whatever the answer at 3 is in the original array. I know math. Cool. Okay, so in the final thing, we can comment out generator. We're just going to solve it. Not going to print that because that's going to screw us up. In here, we're simply going to solve. And the asking is going to be non-def of this, hopefully, unless someone's trying to troll me. And so we print these, and we read in the value, and we should be good. We also have to read in something for the tests, cn to x if x is not equal to 1, x is 0. Cool. Okay, screw it. I don't care about penalty. If it works, it works. If it doesn't, I'll check it out. It's definitely below the query limit. So if it passes the first two, it will pass the last one. I'm fairly sure of that. Oh, that's an old thing. So it passes the first two, it should pass the last one. Guess we'll see. Don't really need this. This is more of an assertion, but I guess it's fine. Cool. Alright, so that basically handles that. Yeah, I'm very sure it's below the query limit because it gets around 16,000 each time, so it should be good. What I'm going to do actually to restore my template is I'm going to take the is this an old version of my rank? I feel like it should be. Is it really that? Huh, I guess a lot of people solve this. Yeah, alright. I'm going to take my old submission just so I can like not have my thing messed up. That got sharply harder. So I guess I'm interested in the last one now. Cheating detection. Alright. Oh. Wow. Randomness. Cool. So 100 players are competing in a 10,000 question trivia tournament. The players are numbered from 1 to 100. Player I has a skill level of SI and question J has a difficulty level of QJ. Each skill level and each question are chosen. Is it interactive? It's not interactive. Good. Okay. Player I has a skill level of SI and question J has a difficulty level of QJ. Each skill level and each question difficulty are chosen uniformly at random from the range -3 to 3 and independently of other choices. Okay, so the probability that they answer it correctly is the sigmoid function. Okay. Cool. Exactly one of the players is a cheater. Is it interactive? 99 lines of input omitted. Okay. Jesus. Alright, cool. So the first line gives the number of test cases T. The second line gives you the percentage of test cases that you must answer correctly for a solution to be considered correct. T test cases follow. Each case consists of 100 lines of 10,000 characters each. The jth character on the ith line is 1 if the ith player answered it correctly, or 0 if they answered it incorrectly. Guess we can like figure out the one that's most unexpected. I'm not really sure. Like, I guess we can figure out the expected value and then figure out which one differs the most. I don't know. I guess that works. I have to like actually download this. Oh my god. It's so much. It's 10,000 lines, isn't it? Or 100 lines of 10,000. Yeah, okay. What the hell? Alright, so n equals 100, m equals 10,000. No way I'm gonna paste this into my, so I'm gonna read that for now. Actually, what I'll do is I'll have that here. just copy this entire thing, put it in here. Hopefully Notepad++ can handle it. Indeed it can. Don't know what's up with that. What? What does that mean? Why are there, what's the 1 and the 0? Oh, okay. So cn to the number of test cases, then to the probability. Don't think we need that, so I might as well just ignore it. So we figure out the expected value for each like person, right? Yeah. LOD tote. Oh, it's random. Okay. All right, wait. Kind of forgot about the randomness. So how? Forgot about the randomness. What am I doing? What am I doing? It's like somehow we come up with an estimate for each player's like skill level or something, maybe. Sigmoid is so weird. Sigmoid is so weird. So what's it like? 1 over 1 plus e to the 0. So it's 1/2 there. If it's 1... So if there's a large difference between the skill level... Oh, -1. Okay, so if it's 2, that's tiny. If it's 3, it's very tiny. So if it's -3, it's very large. So if it's something like -6, it's almost 0. Why am I getting chemistry stuff? And if it's +6, it's a very, very small chance. This is so random. That's the word. So, I guess we can like estimate the skill of each player and then estimate the So is it true that a cheater will always do better than a legitimate player? On average? Say the cheater gets like a really, really low skill level. On average, a normal player will... They'll have it... Like the best players will have at least a 50% chance of doing well always. And... This is such a weird problem. It's such a weird problem. That's all I have to say about it. It's so weird. So like what? So line 50, the 59th line, which is going to be line 61, is the cheater. So I guess it's evident here. So I guess like we can have some sort of estimate for the skill level of every player based on the number of questions they get correct. Maybe the skill level like converges to inverse sigmoid or something, like based on the number, like the percentage of questions they get correct. Because it's random, like the average probability is like point, or it's like 0. So I guess that works. Like we can use the inverse sigmoid to predict each player's like skill and each player's each question's like difficulty. Then for each player, we let's see, what can we do? For each player, we find like the chance they cheated or something, and then we take the one with the highest chance. So how do we like figure out the probability of someone cheating? Well, like for every unexpected thing, like a verdict is unexpected if a cheater like if a cheater does well on a very hard question relative to them, or does badly on a easy question relative to them. So I guess like you can make estimates for the players and the questions. So I'll do mat 105, 10,005. Okay, I have so much stuff here. I might re-explain the first, the fourth, and the last. What am I doing? Okay, so we have a rectangle, a massive rectangle of 100 by 10,000, and essentially, for each player, we'll create an estimate for its skill. Because on average, like the expected, it'd be nice if it was like 1,000 by 1,000, but I guess they don't want to do that. So for each player, we can create an estimate for their skill solely because like how would that be? So it would be, say they get like X questions correct, or say the ratio of questions they get correct is X. So it would be whatever number of questions they get correct divided by 10,000. Then, because there are so many questions, like on average, the average probability or the average skill level will converge to like 0 or something. Because every high difficulty question should be like balanced out by a low difficulty question. So I think like directly for the players, we can use inverse sigmoid to estimate their skill. So we create an estimate for the skill of every player. Then we also, in some other way, we create an estimate for the difficulty of every question. Now, how do we do that? Not sure how loud that was. Just picking stuff off my mic. So we estimate the difficulty of every question. And I guess we could use the skill levels of the players because only one will be thrown off. So maybe we find the... So we find the, let's see. We find the number of questions, the number of people that answer this question correctly. So let it be y. Or the ratio of its correctness, I guess. So this ratio is y. Then we find the a such that the expected value of a is equal to, I guess we can binary search on a. We can find how many? 10 tests? 50 tests? 1.2 seconds per test? That might TLE. I don't know. I guess it's fine. It's a million. Yeah, it's a million. It's fine. So we find the a such that the expected value of questions for a is approximately y. And then this is like, a is like the inverse sigmoid of x. I don't know why I made the rectangle so big. It's not really like pointless. It's pointless, but sure. Okay, now so let's see. Inverse of sigmoid function. I don't need to derive this. Let's just look it up. Inverse sigmoid function. So ln of y over 1 minus y. Okay, sure. It's just, I do not use this function much. Okay, so it's just log. Alright, so the inverse is this. So for each player, or first, I is less than n, I plus plus, cn to string, for loj, actually, let's see, ld tote is equal to 0. I have that. What is tote? What is this? Oh, don't think I need that. For loj equals 0, j is less than m, j plus plus, mat ij is equal to sj is equal to minus 0. So it'll be 1 if it's 1 and 0 if it's 0. Then tote plus equals mat ij. Tote divided by m. Then, so it should be return log of x over 1 minus x. So the estimate for the skill level is inv of tote. Reasonable. Okay. Now let's just print that. Alright, pst I. Should be good. Don't need that. Yep, okay. Values between 0 and 3. Not as uniformly distributed as I would want, but I mean, I guess it works. How good is this estimate? Okay, I don't need to print so many digits. I'll just let this be like 6 or something. I mean, I guess no one answers that good, and no one answers that well. It's not the uniform I would want. I guess it's fine. We sort of need relative stuff. 86 just seems like a random number that's like, do this well or something. So maybe that's probably fine. So now we use the same estimates for y. So for LLJ equals 0, j slant m, j plus plus. Well, the tote is equal to 0. For LLI equals 0, s and n, I plus plus. Tote plus equals mad ij. Make the total. Tote is divided by n. Something like LDL equals -3, r equals 3. What I need the... How much precision do I need? I can get it to like 10 digits with like 30 iterations or something. 30 iterations, half. Yeah, should be good. Probably, yeah. So for might get the first test set optimistically. I feel like there should be a better way to like produce the could do some sort of hill climbing or something. I don't know, that seems messy. This one has a high probability of their expected value would be like huge. Maybe something like this is more accurate. What if we do like double the total? Okay. Something's up with that. Should be good. Nan, what? Is it negative? Oh, it should be between 0 and 1. Wait, what? It's expected value of the ratio of questions they get. Should be like away from 0. It's like we take the sign, we make it closer to 1 by a factor of that. That's what I'm trying to do, not multiply it by 2. That's kind of dumb. We make it closer to 1. So how do we do that? So it's like, if the total is greater than 0, tote is equal to like 1 minus tote over 2. Tote is equal to what would it be? So if it's -1, then it should be like -1 minus tote over 2. Yeah, -1 minus tote over 2. Should give it a better estimate at least. Yeah, that's much better. So 59 should have a very suspicious... Yeah, that's like the largest ever. Wait, am I doing it right? Why is this negative? That feels wrong. Why is it negative? It shouldn't be that. If I negativize this, is it like... What? 59 has a very large... Now I'm confused. The cheater is 59. He should have a very good win rate. Oh wait, okay, right. Yeah, okay. Cheater's 59. He should have a very good win rate. So now everything's positive. Why is everything of the same sign? That makes even less sense. Okay, wait. Okay, you know what? Maybe I should just like solve for this. So y is equal to 1 over 1 plus e to the negative x. Fine. 1 plus e to the negative x. I mean, I probably get the same equation and continue to be confused. E to the negative x equals 1 over y minus 1. So negative x is equal to ln of 1 minus y over y. X is equal to negative ln of 1 minus y over y. Or if I do the same thing, then you get the same formula. Okay, now I'm just very confused. So why does inverse sigmoid act like this? If I get rid of this, is it fine again? Oh, wait. Am I making them all negative? Might be. I'm making them all very close to 0 at least. That should be 1 plus tote. Or not. What am I doing? Maybe it's like 0.5. I'm doing these random things. Actually, yeah, 0.5 is the expected for 0. Okay, sure. So it should become closer to 1, otherwise it should become closer to 0. Yes. 0.5 is the average. Now this makes sense. Yeah, now 59 has an astronomically large probability. So, you know, if I just print the one that has the maximum, it should get it right like 50% of the time or something. Actually, no, that's not necessarily true. What I should do is... I have no idea how to prove probability on this, by the way. I'm just like literally doing random things at this point. But actually, yeah. Printing the one that has the most wins should work when the cheater has a relatively high skill already. So if the cheater has a relatively high skill, which happens like, I don't know, we can say like 10% of the time. If it has 2.4 or higher, it's going to be pretty good already. So then, yeah. Okay, so for each player, let's see. Yeah. Okay, now I guess I have a better way of doing this. For each player, when we're looking for the one that's the cheater, say we have SI, then there's some expected number of wins we get from SI. Now what we can do is we can binary search on the skill value like X. Because when someone's a cheater, half of their losses will become wins and their wins aren't affected. Half of their losses will become wins. So really it's like the X such that the expected value of X, the expected number of wins, plus like the number of wins that they would gain from cheating, which is the number of losses they have divided by 2, is close to S of I. I think we can reverse engineer that, but it's fine to binary search because we have a small number of things anyway. I'm gonna have to like remember what I'm doing because this is so arbitrary. But basically now we're creating sort of a probability-ish of each player being the cheater. And then this weird is like the number of unexpected things we have. So, but first what we need to do is we need to reverse engineer this. We need to find the thing for this question such that the expected value is very close to y. So, it's very close to the number of questions that are gotten correct. It's kind of cool though. You don't see many problems on randomization. This code gem is nice in the way that it does that. So the expected value, how long have I been going? It's only been 2 hours. Okay, that's kind of surprising actually. I thought it's been longer. So like an average code forces round. Okay, I could solve it in like 3 hours if it was a global round or something. Maybe. I don't know if I'll solve it. So expected value of A. So let's compute this expected value. Sum. Oh wait. LDM equals L plus R over 2. Make it 50, 40. I don't know. 40 seems better. Gets like slightly better precision. So for each thing, we compute the probability of doing it. Then we divide it by m. N. If sum is greater than or equal to tot, then it means that our current estimate for the difficulty of the question is more people got it right than we expected. So the difficulty estimate is too low. Wait, hang on. I have to get this right. I have no way to debug this. God, this is going to be impossible to debug. If our estimate for the expected value is too low, that means more people got it right than we expected. Meaning that we should lower our difficulty estimate so that we'll expect more people to get it right. So if our expected value is greater than the actual value, then it means that fewer people got it right than we thought. Meaning that we should raise our difficulty estimate so that we think fewer people will get it right. So we raise our difficulty estimate, meaning that we set L equal to M. This whole thing was for one line, right? We raise our difficulty estimate, meaning that again, just to confirm that the number of people we thought would get it right is higher than it should be. Therefore, we should make it harder so that the number of people we expect goes down. Okay. So now the value is stored in L approximately. And therefore, so the Q estimate is here. So Q est J is equal to L. Right, so now we compute the weird values. So first we binary search on the legitimate thing, the legitimate skill that they would have. So we do the same thing, except like not the same thing. So we can just recompute the same thing, I guess. Doesn't really hurt that much. Okay, now sum is 0. So if sum plus 1 minus sum over 2 is no wait, this should be the expected value of SI. Right, so now we need the sigmoid. LDX return, what is it? So it's 1 over 1 plus, I assume it's exp, yeah, exp negative x. Yep. So the sum should be m2. J equals 0, j is an m, j plus plus. Wait, no, what? This is the wrong place. What am I messing with here? Oh god, what have I done? What have I messed up here? Okay, wait. Did I change the wrong place? Oh wait, no. I never finished that code, that's why. Okay. God, I'm confusing myself so much. I never finished this code, of course not. So the expected value here is the skill of the player. So it's the sigmoid of the skill of the player. So it's p estimate of, so it should be I equals 0. I is less than n, I plus plus. Yep. So it's the sigmoid of the player estimate of I minus, it's the player, right? Yeah, the skill minus the estimate we currently have, m. Okay. This is for each question. Shoot, mid, okay. Can do that. Can do that here too, just to be safe, even though it's not actually necessary. Now this should be j equals 0, j is ln m, j plus plus. Sum plus equals, once again, it would be the sigmoid of mid minus the question estimate of j. Now, if this estimate is too high, and this is straightforward, it means we expected them to get more questions than they actually did, meaning that we expected them to get more questions than they actually did, meaning that we're giving them too much credit. So it means that their skill is too high. The estimate for the skill is too high if they're getting more questions than they actually did. Or if we think they'll get more questions than they actually did. So we set the skill lower. Now that this is the actual skill estimate, what happens? So now we need to figure out like the unexpectedness of certain verdict for a question. So if a question has high difficulty and the player has high skill, we would expect them to get it rather reasonably. What if it's like... So if the difference between the probability and the actual answer is high, then that is... Okay, so for L j equals 0, j is ln m, j plus plus. Weird I plus equals abs mat I j minus the probability of getting this question. Maybe we squared or something? Squaring is arbitrary, but like... The point is that we give higher weights to the ones that are more... we give higher weights to the ones that are more unexpected. And the ones that are expected, we don't give that much weight to. So mat ij minus the sigmoid of, what is it? So it's the player skill, which is L, minus the estimate of that question. Then targ is equal to 0 for each player. If its weirdness value is higher, then set the target to that. And then we print the target. Okay, there's no way this works, but in the off chance that it does, what did I do? Oh, I did not use this because we're doing binary search, so that's fine. In the off chance that it works. Is it really that slow? What? Huh, gets it right. Okay. Interesting. That is very slow though. Wow. I guess division is really not good. How long does this take? If it takes... Oh god, did I select my entire code and comment it? How long does it take? Okay, that's very concerning. Can we get away with that few iterations? Like something like this. If we can speed this up somehow, that'd be nice. What if I did something like made these floats? Float. How much would that speed it up by? Oh, okay, that's a lot faster. Wow, that's insane. Okay, cool. Alright, I guess that works. I guess we could try submitting it. I don't know. Because again, I don't care that much about penalty. So, test is up to 50. So I can do like a bit more of this. Because this is basically constant every time. So first we bring the total closer to 0, then create the player estimate. We create the total, we binary search on the value that would work for this. And then that's good. Then here we once again binary search on the value x, such that if the player cheated, then they would have skill x, or we would expect them to have skill x. Then we square the unexpected probabilities or something. Should at least pass the first test. You know? And again, I don't really care that much about wrong answers because, again, my penalty is down the drain anyway. So we might as well just try it. And I guess I can look over it and debug a bit more. But I'm not really sure what to do here. It's gonna take a long time. It's gonna take like almost a minute. Do we still have this unknown question that hasn't... What the hell is this? This is very good. Very nice design, yes. No, it scrolls even farther. It's like, it says there's a question, and then there's not a question. Like, does that mean I have one question I can ask, and then I can't do anything else? So if I ask a question, it'll become 0 or something? What does it mean? Okay, so we can try other things like maybe cubing it or something. That also maybe helps. Let's see. If I do that, I should remember to do absolute values. Should definitely at least pass the first test. At least the first test. Gets wrong answer on the first test. Okay. That's a problem. What's with that? So we can get rid of this because that's normal. So for each thing. Alright. Am I doing this right? So it's the thing we got, the difference between the thing we got and the yeah, so then we would expect the cheater to have a lot of weirdness. Does pass the sample. That is correct. I'm using test cases, right? Like 100 players are competing in a 10,000 question trivia tournament. Yep, so I'm reading the tests. Yeah. Okay, so that's not helpful. So what's the largest weird value? That's actually kind of close. That's concerning. What if we did like to the 4th or something? What would happen then? So 5, 5, 11. 5, 8, 8, 9. We did something even better. We did that to try and separate the... At this point it's arbitrary things. And I guess that's how it's gonna work. So 88,000. 94,000. Alright, so it's still not that much of a difference. So what am I messing up? So for the expected skill level we would expect them to have if they were the cheater. Oh, wait, I think I'm messing that up. So if they got it, then we would want it to be the weirdness of the skill level they have while not cheating. Wait, how does that work? Yeah, if they got it, then it would be the skill level they would have while not cheating. If they didn't get it, then it would be their normal, it would be their skill level they would have while cheating. think that, yeah, should be better. So 93, 95, 99. Just get rid of the weird 2 times. Does that make a difference? No, it's basically a constant multiple. That doesn't do anything. What I need is for very unexpected things to be weighted a lot more. Does squaring do that well? I mean, kind of, but also like... If we do something better, like exp. I just want to pass the first test at least. I mean, come on. That's even worse. Does that make sense? I don't know if that makes sense. Is there like a... What is sigmoid? Sigmoid graph. Maybe I can use the sigmoid to estimate it. Inverse sigmoid graph. Actually, that shouldn't be that interesting. Yeah, it's not really that cool. Okay. So like maybe if I did the sigmoid of this to... Was that their hint? Was that their hint to use this for like the probability of like weighting things higher? So like 6900. It's barely better at all. No, that's even worse. Don't think that helps. Okay, I can get rid of this. Maybe I make this like a higher power. This is me just doing stupid things on camera. Pow of x to like the 20th or something, or like to the 10th. How much does this help? So 2039, 4260, 4300, 4600. I mean, it is somewhat better. Okay, I guess we're gonna have to generate some data. Right. So we're going to generate to, so I can generate to test case 2. That'd be better. So I can put this here for now. Then put that there. Now for LL equals 0, I less than 100, I plus plus. Actually first. So pi is equal to I guess I can do like LD, R and D. I know it has to be between -3 and 3. So actually no. It's like something like float RNG mod something like 100,000 or a million over a million. Times RB minus LB plus LB. No, wait. Yes, plus LB. Okay, so Rn range -3, 3. Qi. If Rn range 0, 1 is less than or equal to the probability, which is the sigmoid of pi minus qj. Alright, actually, that should be it. See out, because that'll convert to a 0 or 1. Make the first player the cheater. If I is not equal to 0, else either this or that, or the coin flip. Okay, so now test case is something else, I would hope. Or not. What? What's happening? Send out. This is kind of a pain. Okay. Why does that work and the other one doesn't? Okay. Column 10,001. Perfect. But the length is 1,104,000. That makes sense. Okay, yes. Each new line is an additional thing. Alright, now I get rid of this and I test it and see if it works. Or see how it works. Gets 1. Okay. What's the estimate? So it has a ridiculously high win rate. Yeah. Try it again. Alright, it should be void. So what's the probability of 1? Still huge. Is this basically coming out to just whichever has the highest thing? So if I do this, it just won't work or something. By the way, comp R is just like compile and run at the same time. Okay, so it basically, yeah, it basically comes down to whoever has the highest estimate, I guess. Yeah, okay, well that's dumb. So there should be something better. Like it has to involve the probability somehow, right? Why is it converging to highest estimate? So we create the question estimate for each of those. So if they get it, then it's the... So this should be like... The weirdness is the probability that they don't get it. If that is high, then... If they got it and the probability that they didn't get it is high, then that's unexpected. And if they didn't get it and the probability that they would get it is high, that's also unexpected. How's this? How is this working? Is it actually working? It's always -3. Oh god, okay. Right, because I forgot to do this. Oh my god. That's stupid. Still -3. Because it should be M. Yep. Okay, now it gets a different thing. So it's not the best, but is it still... Why is it always -3? How is it -3 for even that? That's weird. Tot plus equals mat ij. So if it got it or not, then... So if our estimate is higher, there's no way this is -3. Tot. That can't be -3. How would it be -3 for positive numbers? How? So, cout it sum. So like, for example, what am I getting here? The sum as expected for 0 is around 5. Okay. So it would be around 75. Okay, that guy, wait. Okay, actually it does have a very low skill level, so that's fine. Maybe we don't cap it at -3. What if we do something like that? That makes it even weirder. What? If it gets to -50, I know there's a problem. Okay, there's definitely a problem. Like if I make it higher. Yeah, I must be doing binary search wrong. Wait, if I change it to not float again, like, if I make it double or something, does that do better? It's gonna take longer, but, I mean, correctness is also important. Oh, wait, I see. Okay, so I think we can ignore the people who have like roughly less than 50% probability. So if tote is less than or equal to 0.45, then just ignore it, because that's sort of pointless. Okay, sure. Feasible. I don't get how does it gets this small though. 0.5035. What does that mean? So 0.035 would be, or like 0.070 would be the expected without cheating. That's insane. Wait, there's no way that's right. Is it? I guess it would be if their skill level is very low. Why is it that low though? 1 over 1 plus e to the negative 3. I guess it is really that bad, huh? Okay, sure. That is some noise. Indeed it is. Okay, that is definitely some noise. That's for sure. Also, why is it not roughly half of them that are eliminated? So wait, 1 is terrible. So it really doesn't think that 1 is cheating. Okay, my cough has been a mess this whole time. It's probably going to continue to be. So we get an estimate of like slightly on the negative side, which is fine. That's what we expect. So if they cheat, then half of their solves are very unexpected. If they got it, then how weird is it for them to get it, right? So for example, 7, which has a total of that. So is that what's causing it? Does 67 have a negative 50? Yeah, it does. So if we ignore all the ones with negative 50, so if L is like less than negative 10, continue. If R is greater than, so I guess we can just like basically eliminate all of these, right? Because this probability of happening is so low. It's greater than 10, continue. Those are like creating outliers, basically. I guess that's the problem. But another problem is that it still really doesn't like this one. R is greater than 10. Yeah, it really does not like that one. And the question is why? So if I enumerated all of them, that would not be nice. So this guy should get around half of them correct, regardless of what happens. Will we factor into account like how weird is their current performance and how unweird is their usual performance? If we just like totally ignore this. I don't think that makes sense actually. No, that's not right. This should be P estimate of I. I feel like that wouldn't fix things, but I don't know. Yeah, it wouldn't. It's like if they got a question right, then either they cheated for it or they got it legitimately. If they cheated for it, how probable is it that they cheated for it? What I could do is also try and make sure I'm doing this right. Tote L and L. That's going to be a lot of output, but do we also get some problems here with this sort of binary search? Like, do we get negative 50s and 50s? Okay. Right. So ones with higher rates of being solved have lower difficulties, as expected. Okay. Now this is something I could optimize, but not this. Yeah, I could optimize it to be 100 squared, but that barely matters. I don't know if it's bugged or if it's just like wrong. That's also the thing. This does seem like abnormally high though. We'll say that. Something is 0.07, then it gets a difficulty of huge. Why am I scrolling through these? What am I gonna get out of scrolling? So why is it so weird? Is it because there's one cheater? I mean, wait, theoretically it should map to a value between 100 and negative 100. Oh, right, no. No, I mean 3 and negative 3, but I guess not. I guess it doesn't have to. This could be interesting. How distributed is this? What? What happened? Oh, I did not do semicolon. Does that work? So we do get a lot near the center. Guess that is roughly expected. Sure. Weird that it's like mostly around the ends. Wait, how's the... Oh, no, never mind. Is that weird that it's mostly around the ends there? I mean, actually, this is just the raw data itself. So if it's weird, it doesn't really make that much sense. So I make this negative 3. What happens? It's not really... Don't need this. I could use that. So 1 is like... has a total of... Wait, oh, I need to generate it. So does this get even worse now? Has a probability of what we expect around 55. What's 86? These are still outliers, aren't they? What if we just get rid of that? Get rid of stuff until it works. Okay. Well, let's try a few more things. For example, if I set this to be 0. Maybe I should weight the getting it wrong ones lower or something. Because the problem is like these outliers, the ones that had almost no probability to be cheaters at all, we're getting like massive weirdness. Maybe if I changed it to that, it'd be better. These are all just random heuristics, of course, because what else would I do with my life besides come up with random heuristics? Okay, so it's 68 again. And it's because the probability is still so weird. If I set this 3, we'll certainly get it. For sure. Oh, really? Wow. What? Maybe not. Maybe it has the best chance of getting it when it's really low. Okay, that's an insanely low chance. What? I guess not many of its things are affected. This is not a good metric, that's for sure. That is for absolute sure. So I should find a better way of doing this. It's probably gonna get one, yeah. What am I expecting? I have a cheater with -3. What am I expecting? It's like 0.55. So if I do that, I should have a pretty good chance. So I generate it again. Yeah, okay. So maybe this will now work for the first sample, or for the first test. But it's definitely not going to work fully. Yeah, because the ones that are unlikely have so much more weight. The ones that have very few solves in general. And because, like, why wouldn't they? Well, but the thing is, their solves would be on... Their solves would most of the time, be on the ones with lower difficulty. But the solves for 1 are almost random. Well, the ones with lower ones, like for example, let's take, what did we take? 22 and, let's see, 63, 65, and 80, maybe. Do those all fit on one screen? 63, 65, and 80. Wait, what? Something's messed up. So this is line 1. We are counting from 1. Oh, 64 and 66 are gone. I see. So take 63, 65, and 80. It's going to be impossible to compare, but... Alright, 82 is the one. And 67... Nope, okay. That's not going to work. I expect them to be similar. Meanwhile, one gets like totally random verdicts. This would be like better than between 0 and 1. Maybe that's the problem. Actually, if something has a very low probability, raising it to the 10th will almost certainly destroy it. Am I still raising it to the 10th? Is that what I'm doing? Someone has a very high skill level. They have a very low skill level. And a lot of their solves are going to be like unexpected. I just don't get why it's so like similar. Like for example, 65. A lot of its solves should be expected, right? Maybe I sum up like 1 over their probability. 1 over their probability of... One over the probability of it happening. I think maybe that's what I'm looking for. I just can't find the right function for this. Maybe 1 over the probability of it happening is a good metric. Nope, apparently not. Does that work better for other ones maybe? So 0. I would imagine it wouldn't. It does not. Yeah, 22 is much higher. I don't know why. Because most, wait, if this is, if this is 0, most of these solves are like half chance maybe? Could also just make it absolute. It's also something to try. Still don't know at this point. Might also be just some better way to evaluate it. 22 is still considerably better, yeah. I guess the reason is when someone's close to 0, like, most of their probabilities are pretty tame, I guess. I feel like it's a bug or something. So we read in the string, we take the total, divide it by m, and then we bring it closer to 1, maybe to make the probability. Is this screwing me up? I don't even know. Not that much. How much does it affect me by? Yeah, it's like barely anything. Okay. Let's create the total for each column. Don't really need this anymore. Divide it by n. So we binary search on the appropriate difficulty for each question. Similarly, something like this would be more effective. And this expected value is simply the probability of getting it. Then if the guess is too high, anyway, it seems like it would work. If the guess is too high, then more people solved it than we expected. So we should make it so fewer people solve it, so we should raise the difficulty. Yep. Now for each person, we find the actual value it gets. What if we just like take the difference between the expected questions they get? No, that doesn't make any sense. That would be... What if we just do that? What if we just take the difference between like the expected questions they get, oh wait. Let's be like the expected questions they get with their non-cheating probability. Well, it sort of comes out to the same thing though, doesn't it? Like if they got it, how unexpected is it? Or if they didn't get it, how expected is it? Can we just count them? That could work too. I think that was my original idea actually, and then I just like dropped it for some reason. If Matt IJ, so if they got it, and the probability of them getting it while not cheating is less than some threshold, say like 0.1 or something. Is that a good enough threshold? Not really sure. Maybe like 0.2 plus weird I. Else, if they didn't get it, and the probability of them getting it Alright. If they got it and the probability of them getting it is less than a threshold. If they didn't get it and the probability of them not getting it is less than the threshold. Does that work better? Probably doesn't. Is there some value that optimizes this? It was 22 just like destined to be? I do not understand this. Don't understand this code, I don't understand this problem, I don't understand anything. If we've been for 3 hours now? Yeah, we have. Okay, that's unfortunate. Just print some random values. So what's this gonna do? Wait, what am I trying to do? I actually don't know. Somehow I thought this was a smart thing to debug, but I don't even know what this is gonna do now. Maybe it's just like printing some random probabilities or something. Did I mute? No, good. Like, I have no idea what this is doing. I mean, it's just printing some random stuff. If we specifically print 22. Wow, are you kidding me? Wait. Is it actually just barely not enough to have that? Are you serious? Okay. So 22 is 1.24049. So that's the estimate based on only their values. Wait, what? Did these make sense? 5.5. If someone has a probability of 1.2, maybe this is screwing things up. I don't know. What if I fix that? This makes some sense. Not really sure. I'm not very sure. Okay, we just gotta like reevaluate the strategy entirely. This just sucks. This is not working. Should have said that a lot earlier, but man, I don't know why it's not even like trying with the current values we have. I mean, okay. Me an hour ago thought this was logical, so it's me an hour ago is probably smarter than me now. So maybe I should keep that. How big a difference is it? It's much better. Is that what I needed all this time? Probably won't work here, but I just need to consider the original probabilities. I could just try this. I think it'll only work for like the smaller values, but it can't hurt to try, I guess. Because again, once again, penalty is absolutely out the window now. So it's been almost an hour since, it's been basically exactly an hour since my last submission. Unfortunate. Was this TLE? Wait. Wait, I used doubles, didn't I? Huh. I guess long doubles are just that much slower or something? But if I make this long double... Oh, or float's the same size, maybe? Really is that much slower. Wow. Okay. So again, I think it should get the first case, maybe. Has a decent chance. Guess I can try some more of these on my own. So I set this to 1. Yes, what? I'm not done. Okay, so that still doesn't work. And it's gonna take a long time, I would assume. Shouldn't take more than 2 minutes. Is it TLE? No, if it was TLE, it would be done already. So I guess it's running them both and doing some stuff with it. Oh, it does get TLE. Okay. Well, in that case, we do float. Don't think we need so many iterations, probably. Can do something like that. Would this be like 10 or something? In fact, I don't think we need that many iterations at all. We can probably have this be 30 and still be fine. It's using floats now. Okay. Sure. That still doesn't get rid of the problem that the algorithms is pretty bad, which is like a pretty significant problem. So it's like we're basically counting the number of unexpected results. Does this work for a random 0? Maybe this works like 50% of the time or something. If I make it less probable, what happens then? The problem is at the higher skill levels, it doesn't affect that much. Still gets wrong answer. Okay. Am I handling multiple cases right? I am not. That's why. That would make sense. Mat, PS, QS are being reset. Okay, yep, not handling multitests right. That is also a problem. Estimates are set each time, so that's fine. Matrix is read in. The only problem is weird should be reset. Yep. Wait, do I have some weird debug mode on? Hope not. I did set the probability lower. Wait, did that work? Wait, I don't... Okay, no. It's a bit too excited for that, unfortunately. Yeah, so basically useless. So we finally do get the first test set. Where does this put us? I mean, I feel like it's not that hard to get the first test set either. Alright, it's not the worst. It's not the best, but it's not the worst. So that's pretty good. How are people doing? Yeah. And then like everyone pretty much saw this. So how do we do better for the higher probabilities? Work on average for a decent percentage. Like if I make it like negative 0.5 or something, should probably work pretty well into that. Yeah, it gets one. So, alright. So how do we solve it for high chance? So with a higher, if I just make this even lower, the number of very large anomalies. Does it still work if I do this? What if I just like keep setting this lower? Will it work here? Oh, that's not intended. No, pretty much no. Why is that the case? Shouldn't it be true that there are many things that are very unexpected if that happens? I think this is too high. Set it higher? No. Maybe I should bound these again because this seems like it's actually important now. If I make this lower, 0.05, which is not that great of a probability. I have to set it to the 1 over 1 plus e to the negative e to the 2. So it should be like around there, 0.13. Okay, that doesn't help. That's not good. So if it already has a very high skill level, then on average like an eighth, wait, 1 plus e to the 0.75, that's like an eighth of them over 8 times 24. So we should get like a decent like maybe 1,000 or so about of the unexpected ones, or 1,000 over 2. Should try printing the weird values again. So what's being prioritized? 43, which has 477, and one has 316. So the skill level doesn't change that much is the thing. Somehow we have to account for the fact that at lower probabilities, higher probabilities, the unexpectedness will be lower. Maybe that's interesting. What if I do something weird like this? Some other weird heuristics. Weird I. Or wait. If I do this instead. One minus sig past I. Alright, if I divide it by that, then that means that like the higher ones have better chances. Now if I go for the lower ones, maybe that becomes a problem. Wait, how much of a difference is it? Oh, it's like significantly better. Maybe this is the key. I don't know. I kind of just want to be done with this problem, to be honest. This is painful at this point. Okay, how effective is this? Maybe it just works. Maybe waiting by that works. Okay. I guess that is sort of a significant thing, that we do have to account for the fact that it's going to be less frequent when we have higher values. See how that works. Maybe it does, maybe it doesn't. I guess we'll see. If not, I can adjust my heuristics a bit more, but it does seem like it has a pretty good chance of working. Like I tried some of these high probabilities. So I do, for example, this. Comp R. Comp R. Wow. Wait, this could just work. Okay. It's working for like a lot of things. Does it stop working for small things now? Maybe that could happen. Works for that. This could just be right. Alright, I would hope so. Because then that would let me be done with this problem. And I would like to be done with this problem. Not that it's a bad problem, I'm just like not that good at it, so... Okay, cool. Alright, I don't know why that worked, but it did. So that puts me in 157th. I had a decent amount of penalties, so I don't think my rank should go down that much. How long did it take? It took around, let's see, 3 hours and maybe like 30-ish minutes. I don't think this took that long. So maybe, actually I can measure that here. Yeah, around 3 hours and 30 minutes. We had 5 penalties. One of them was a joke penalty. So if I was seriously competing, I wouldn't have done that. So we can discount that one. So 3 hours and 30 minutes is 210 plus 16, so 226. 226 over 60 would be around 3 hours or 2 hours and 45 minutes. A penalty. So see where that puts me. 2 hours and 45 minutes. Okay, cool. So if I was doing it from the start, or wait, no, 3 hours. 3 hours, not 2 hours. Okay, bit optimistic. But if I was starting from the beginning, this would be what I get. So that's pretty good. That is very good. I am totally happy with that. Don't really get why this works, but okay. Let me just think on this for a bit. I don't get it. I don't get it. I don't get it. I really don't get it. It works, but I don't get why. I have no... What? Just what? Just what? That's what it is. Just what? Also, I'm fairly sure I'll get this. I'm fairly sure I'll get this. I'm fairly sure these are good. So, should be good. But just also, what? Alright. Whatever. I'm going to just go over these solutions to the ones that I did not think I explained that much. So this would be the first, the fourth, and the fifth problem. Since I just did this one, let's do this. Alright, I may or may not be reading through my code also. So I'm not gonna read the problem statements. You get it. You can read problems. If you misunderstood it, then try to reread it. So the first step is we're going to estimate the skill level of each player. And the basis for this estimate is that basically because we have so many samples of questions, the average probability we're going to get is roughly like the average skill level or the average difficulty of a question will be 0, and it'll be very close to 0. So using that, we can basically take the value x, the number of questions they get right, and then divide that by 10,000 because so we get p, for example, the ratio of the number of questions we get right to the number total. Then we use that to estimate the skill level of this player. So what we do is we basically first we bring it a bit closer to, we bring it farther away from 0.5. So if p is here, then we would move it a bit towards 0, and if p is here, then we would move it a bit towards 1. Now this is just sort of because of the way the sigmoid will work, it's sort of it's a bit skewed, so it's not going to perfectly represent the values. And in fact, I'm not sure if this is necessary. I don't think it's that necessary because most of it's relative anyway, but this just sort of makes it a bit more accurate, I guess. I don't know. I don't actually know if it does. Maybe. But this is just what my solution's doing. So if p is greater than or equal to 0.5, then it becomes half closer to 1. So it closes half of the gap between it and 1. So it becomes 1 plus p over 2. So it's the average of itself and 1. And otherwise, if p is less than 0.5, then it becomes closer to 0. So it becomes 0 plus p over 2, or just p over 2. And then you can get the player estimate by simply taking the inverse of the sigmoid function. So the skill level is the inverse sigmoid of the probability. Because this is sort of basically the average probability that we get of solving a question, where we assume that the average is sort of close to -1. So I'm not really sure. I don't know if this whole thing is necessary. There's a good chance it might just not be. I remember I had some good reason for doing it, I think, or some reason that I thought was good, but I've forgotten it now. So if you want to know why, maybe just watch the screencast. I don't know. What? Wait, why did I do that? What was the point of doing this? I don't know. Why did I do that? I guess it was because maybe taking the average of the scores is I don't know. I have no idea. So if something has a 0.6 probability, for example, or a 0.8 probability, then it would roughly get Oh yeah, I guess that's why. It's because the average. Okay, I remember now. It's because the average is a 50% chance. like the average question difficulty gives you roughly a 50% chance for the average skill level. So if you have a higher skill level, then like you want to make it farther away from 50% because the average is 50%. So you'll on average like get lower scores or something. I don't know. It sort of doesn't make sense, but it's doesn't. I don't know if it makes enough of a difference to matter. But essentially, the point is we take the number of points they get in total, and then we make an estimate for their skill level as the inverse sigmoid of this modified number of questions they get correct. Now, it's harder to do the same thing for questions. It's going to be less accurate because we have at most 100 players, or exactly 100 players. But now we already know the estimates for the skill levels of the players, so now we can use that to determine the estimates for the skill levels of the questions. So basically, we binary search on the value qi. And the way we do that is we pick qi such that the expected number of solves on this question with this difficulty level is equal to the total number of solves. So if this was x once again, if we had x solves on this question, then it would be x over 100, which is the ratio of the players that solved it. Or that answered it correctly, whatever. I'm going to keep using solve because that's what I'm used to. So we binary search on qi to find the qi that makes the expected value of the players that get the question right equal to the number of players that actually did get the question right. And so like the reason this works is, I mean, because like that's the best estimate we have, and to get the expected value, it's simply like, because getting a question right is 1 and getting a question wrong is 0. Wrong is 0. Then the expected value is essentially a sum of probabilities. So it's essentially the sum of, what is it? So it's sigmoid of pi and qj, for example. Or like for some other player, it's the sum of that player's probability of getting the question right. So we can binary search on this, as I do in my code, and then that gives us an estimate for each question. So now we do this absolutely weird garbage magic of whatever the hell my evaluation function is. It's so stupid. I don't know why it shouldn't work. I don't know why it works, but it does. So in fact, none of this is necessary. All of this is completely useless. All of this is useless. This is the only part that's relevant, I think. Right? Just make sure it compiles. Just safety check. Yeah, okay. This is the only part that's relevant. Basically, we figure out the number of like weird things that happened. So consider some player I and some question j. If they get this question right, but the anticipated probability of them getting the question right is very low, like below some threshold. So if the sigmoid of, actually this should be minus, not comma. It's the probability of, I mean, if you read the statement, you'll know what I intend to mean. It should just be that. So if they got this question right, so if the matrix value here is 1, but the probability of them getting that question right without them cheating is below some threshold, let this be x. In my program, I used x equals 0.13. I'm not sure if it matters. It probably does. I think 0.13 works so well because it's like very close to 86 or something. I'm not really sure. But the idea is, I think you can try some other various x's and see if that works. So if it's like improbable that they would have gotten this question right normally, then like add to a counter. add to a counter of the number of like, that's suspicious questions that we had. And then similarly, if they got it wrong, then we figure out the probability of them getting it right, which is 1 minus the probability of them, sorry. If the probability of them getting them wrong is suspiciously low, and they did get it wrong, then we also increment the number of suspicious times that things have happened. So that's essentially what this does. And of course we should take the absolute value, which I think is already done, so that's not really necessary, but that's fine. So now the problem is that cheating, when you have a very high skill level already, cheating doesn't do much for you. Say like PI is equal to 3. So on average, you're going to win around like, I think it's around like 97.5% of games already. I think I can look at this and see. Okay, that might be an overstatement, but actually no, that's definitely an overstatement. You'll win like maybe like 85 to 90% of your games, or the questions, whatever, right? So the effect it's going to have is it's only going to change around like 5 to 7.5% of the verdicts, because it changes exactly half, or it changes, not exactly, like it changes on average half of the wrong answers to right ones. So that's a problem. So because the number of anomalies is going to be much lower when you start off with a high skill level already. So what I did was I just like weighted by their skill level, where a higher skill level would weight the anomalies much more heavily. And so the way I did that was I simply took the total. So you take this total and then you divide it by their probability of getting an average question wrong. So the average question, again, has the expected difficulty of 0. So the probability of getting an average question wrong is 1 minus the sigmoid of the player's skill estimate and 0, minus 0. So then because this is always less than or equal to 1, a lower value of this is going to mean you get more weight. So the very high skilled players will be weighted much more simply because there's less of them to look at in the anomalies. And I'm sure you can like actually compute this value, I'm pretty sure. And then you could figure out like how much to weight exactly, but this heuristic works well enough, so it's fine. And yeah, then we weight that, and then we simply pick the element with the largest total. I'm not sure what its probability of success is. I'm not really that interested in measuring it. If you want, you can find my code. It's there. So yeah, that's it. Cool. I should fix that at some point because it does keep notifying me about that. But anyway, yeah. So I think it has obviously it works pretty well. It gets the case right. So it works more than 86% of the time, which is pretty good. Yeah, it's the basic idea. This solution is a mess. I'm sorry. It's just, I don't know why it works still. I just did a bunch of random things, messed with a bunch of stuff, and eventually it just got the checks. And so that's it. That's all I know. Has my rank gone down a bit more? Yeah, as expected. Alright, so I did again explain the second and the third. I did also explain my idea for the fourth, but I will do it again, just like with more detail. So basically, the strategy for this is we don't know anything from the start. So we might as well just like pick any two elements, right? Okay, what do we do with that? Well, so what we can do is, because it's randomized, if we use these two elements as anchors, kind of, and then we figure out where all of the other elements are relative to these two, then on average, like there are 3 places an element can be relative to these. Also, we can assume that like 1 is less than 2, because if not, then we'll have the opposite, and that's fine. It doesn't matter if we have the opposite. Or like the reverse, I mean. So we assume 1 is less than 2. Or we assume A1 is less than A2. Meaning that what we want to do is, there are 3 possibilities for elements. 1, they can be less than 1. 2, they can be greater than 2. Or 3, they can be between 1 and 2. And in fact, if we query for each I the position of 1, 2, and I, if we query the median, if the median is 1, then that means that I has to be over here. If the median is I, then I has to be over here. It has to be between them, by definition. And if the median is 2, then I has to be over here. So with the query of this, we can determine exactly where I is supposed to be in these 3 sort of buckets. So we can do this partitioning into the buckets with at most n-1 queries. Or actually, in the first step, it's n-2. In general, it's n-1, because we also need to determine the order for smaller cases. And so for the first step, it takes n-2 queries. And we figure out what happens. We figure out like which of these buckets each element is in. Then now, because we know we have a splitter element 1 and a splitter element 2, where we're certain that these elements have these positions relative to these 2 splitter elements, we know that we can solve these buckets independently now. They're independent of each other. No element in one bucket will ever cross with another element of another bucket. So really, we have 3 independent subproblems to solve for. And now we also just got rid of 2 elements, which is cool. So now, say we're solving for an independent subproblem. There's a bit more complexity involved, because now we can't, so assume we're solving for this. Say, like, for example, the numbers 3, 4, bunch of other things went into this, right? So we can pick the first 2 numbers that we got, for example, 3 and 4. The problem is we can't automatically assume 3 is less than 4. We could do this initially because we're allowed to have the reverse of the array, but now we've fixed the direction of the array. So if 3 and 4 is here, and if we reverse that, it's going to be a different array. It's not going to be the exact reverse of this. So we need to figure out whether 3 is less than 4 or 4 is less than 3. It turns out we can do that with a single query. At every point, we simply maintain the parent that got us here. So we maintain the parents of the blocks that were in the 2 surrounding elements. And so we can also stick like a virtual -1 on each of these, and then we only use parents that aren't -1s. So when we know we have some parent over here, let me move this over slightly so that I can show that we have a parent. So for example, actually I'll do both. Yeah. So when we know we have a parent, for example, B and then A, what we do is, if this parent exists, then we can use it to compare these 2 elements. Specifically, we can say, if we query these 3, whatever's in the middle, whatever the median is the smaller one. Because we know this is the smallest. So the median's going to be in the middle, and then the other element has to be larger. So we can determine which one's larger. And then, if this parent doesn't exist, if it's -1, then we know we have to have this parent. We have to have at least one of the parents. And note that like the distinguishing factor for the first case is that we don't have any parents. But it also doesn't matter if the array is reversed or not. So if this is -1, then we query these 3. And now whichever one's the median is the larger one, because we know this one's larger, so the other one has to be smaller. And so the one in the median has to be in the middle, so it has to be bigger than the other one. So now we can compare 3 and 4, so we can figure out which one of these should be on the left and which is on the right. Now without loss of generality, assume this. If not, you can swap 3 and 4 and you'll get the same strategy. Now we do the exact same thing. We query 3, 4, and I for all of these. And that's it. Now we have these even smaller independent buckets, and now we can solve independently for each of these, and we do the same strategy, and we continue on until we're done. Now you can use these parents for the parents of the smaller buckets, or you can use the negative ones. It doesn't matter, because all that matters is that there's at least one parent that we know about. So every bucket will be adjacent to either the 3 or the 4. And we can use that parent to figure it out. We don't need both parents to be alive. Disney moment. Yeah. So, cool. That basically settles it. That's a disgusting arrow. Can I salvage it? Kind of. Close enough. Right, so yeah, that's it. So we break these into buckets, then we solve for these buckets recursively, and the base case is if we have 0 or 1 elements, in which case we automatically know the order, so we can return immediately. Then when we solve for all the buckets, we simply merge these into one huge array, and then we return, we merge everything into one large array, and then that's going to be our answer. So how many queries does it take? Well, it would take on the order of n times log base 3 of n, because at every point we split by 3, so we go from n to n over 3 to n over 9 to n over 27, etc., up until it becomes 1. And so that's like the definition of log base 3 of n. So that, my god, I cannot write letters, or numbers. Can't even write n's, like these are just blobs. I don't even know what they are. So on average, it would take that. And because it's random, we're going to get the average case almost every time. So the randomness makes it nice because we don't have to worry about the worst case. We're interested in the average case now. Oh, God. Huh. Jaw. Talking too long. That was a fun noise. So if we do a quick Google search or just a calculator or whatever, we get log 50 over log of 3, which is around 3.5. If we multiply that by 50, we get around 178. So that will certainly solve the first 2 subtasks. The question is, does it solve the last one? And the answer is yes. So we need around 170 queries. But the thing is, it's going to do better because at every point, we remove at least 2 of the elements. So we don't use that like every time. So it's really like, it's something like n plus like n minus 2 plus like n minus 6 plus like n minus 18 or something. Or, yeah, n minus 18 and so on. So that's going to be a constant optimization. Maybe we get 3 or 4 levels. Another thing that happens is that for every point, it only takes, like if we have a bucket size of b, it only takes b minus 1 queries to resolve a bucket. Specifically that like we need 1 query to determine the order of these elements, and then it takes m minus 2 or b minus 2 queries to figure out the rest of the elements where they go relative to the buckets. So that's going to be another optimization. And in general, like, even if the randomness makes it so it's not a perfect split every time, it does pretty well regardless. So on average, what I was getting around 162 to 164 queries. This was my code, testing my code. So it was getting around 162 to 164 per test. And that's certainly enough. So, or like an average of that per test. So it's well below 170. It's probably going to be fine. So if you implement this, it should be good. Now, for the one that I have yet to explain, this one. Did I explain this? I feel like I did. And like, this is basically as straightforward as it gets. You have an array of numbers, and you basically implement the algorithm. You find the index of the minimum, then you reverse the whole array using some reversal algorithm. For example, in C++, you can just do reverse the left pointer and then the right pointer exclusive. So like this would reverse the open interval on the left and the closed interval on the right. So like you reverse it. Another way of reversing is simply like if you're reversing an array of length n, you split by the midpoint and then swap every element with the corresponding element on the other side. So for example, if this is 1, this is 2, this is 3, then this corresponds to element 5, which is like n minus 3 plus 1, and n equals 7. Then this would correspond to 6, which is n minus 2 plus 1. And in general, the element that corresponds to I should be swapped with n minus I plus 1. So that's the way to do it. You can simply just swap these until you're good. I'm sure many languages have a built-in function to do this, so it's probably not necessary. But either way, anything basically works. And then once you do that, you compute the cost of the interval, which is simply the length. So if this is position I and this is position j, then the length would be j minus I plus 1, because it's j minus I, except you have an extra element because you're like counting the endpoint. So that would be the cost. Then you simply do the reversal, move on to the next index, and do the exact same thing. So basically, it's just writing code to do it. Should be relatively straightforward. I mean, if you look at the code, basically read in the array. So find the index. In C++, again, there's the reverse function, and then you add the length of the array. So that's it. This took way too long. I am not... This took way too long. But it also, like, my solution's basically trying random things, so... Did my rank go up? Oh, did someone resubmit? I guess they must have. Cool. Yeah, that settles it. So that's basically everything. I hope you enjoyed. I hope you got what you needed out of the video. Even if you... I mean, nobody watches the whole thing. It's like 4 hours. Don't do that, please. You have better things to do with your life. But... I mean, yeah, hopefully you're able to get what you need, or at least like solutions, stuff like that. And yeah, this was Code Jam qualification. Cool. I have nothing more to say. I'm just too tired to end the video. So yeah, I'm assuming the video lagged at some point. If so, I'm sorry. Not really sure what to do about that, but okay. I also need to get used to my face cam like blocking things. At some point I'm gonna have to shrink this and just make things work. I'll get used to it eventually. If there's some trouble, just leave a question in the comments. I'll try and resolve it. Alright, goodbye.